Okay, electronics. This is my cheat sheet. You should be able to feel pretty comfortable with some of these formulas, but I think the key to electronics is kind of practice. It's not really the formulas, it's how to use them. So a cheat sheet is less useful here than even projectiles. Projectiles is pretty useful. Here it's a bit less useful. But we'll go through them anyway. So you should be comfortable with voltage equals current times resistance and all the other versions of that. Resistance in series. So just quickly, we have this many resistors in series, the total resistance equals 2 plus 2 plus 2, R1 plus R2 plus R3, equals 6 ohms. Great. Resistance in parallel, if we have this, I'll put another one. They're all in parallel. Okay, our circuit's like off here, and there's a battery. Okay, there. Now, what's the total resistance of this? We just use our resistance in parallel formula. Total resistance is the inverse of the sums. So 1 on 2 plus 1 on 2 plus 1 on 2 all to the minus 1. Total resistance equals that. Equals 3 on 2 to the minus 1. Equals 2 on 3. To the minus 1 means just to flip it. 2 on 3. So that's the total resistance. Or for those of you more comfortable with decimals, 0.66 ohms. The voltage divided formula, I'm just going to go through it quickly. Essentially what you want to do is get the resistor, the resistance of between where you want to measure. So you want this voltage, figure out what the resistance of inside is. And then you divide it by the total resistance, and you multiply it by the voltage coming in. Before you can do anything here though, you can't just use 2. 2 would be the wrong answer, because the resistance inside here is not 2. Even though we're measuring across that, it's not 2. We have to convert this to a single resistor first. And we do it here, placing with a single resistor gives us, using our parallel formula, 1 ohm. This is essentially 1 ohm effectively. Now we can apply the formula. Voltage across here equals 1 divided by 1 plus 3. The total resistance 1 plus 3. 4 times the input voltage 6 equals 1.5 volts. Easy. Diodes, not so easy. This confused the heck out of me for last day or 2 or 3, or actually I've never learned it until the last 2 days, but I spent a bit of time learning about P and N and all these other things, but you don't need to know all that. What you do need to know, however, is that diodes look like this. In general, most of the time, they send electrons, they send current this way, not electrons, current this way. So let's look at the light emitting diode first. If we have a battery connected here, and it goes through like this, then the current is going this way, and it's going in forward direction. So we call that forward bias, and that's how we use LEDs. Diodes have very funny current versus voltage graphs. Normal resistors have current graphs that look like this. Okay? Where the voltage is proportional to the current. And they call this ohmic. Diodes usually aren't ohmic. That's not a straight line, it's not ohmic. So this is not an ohmic resistance. It's a diotic. I don't know what they call it. It's a diode though, and it has a funny resistance. And the graph tells you what voltage is required. And that's really all you need to do. You look at the graph, you look at the little schematic, and that should be able to solve your question. So you have to use them in forward bias as well. Here is a question from 2009. This is our LED. This is our graph of the voltage versus the current. It's all there. And it looks just like that. Now, he sets up a circuit involving 6 identical LEDs. What is the value of the current through R2? So we can't just go 12 volts. We can't just use this straight away. We can't just say 12 volts is dissipated in there. We have to know how much voltage, because LEDs usually take up voltage and dissipate in each of these. And for that, we looked at the graph. You notice here that at 3 volts, that's when it lets current through. Before this, nothing will happen. There's no current going through. This circuit won't even work. So we know each of these has to take up 3 volts. Some of you may think, oh my god, that's too many volts. It's 9 volts here, 9 volts here. Remember, when you get to here, both sides get 9 volts. You only need 9 volts here, because voltage doesn't split. It doesn't become 9 doesn't become 4.5, 4.5. It's only current that splits. Half the current will go this way, half the current will go this way, but they all keep 9 volts. So up here there must be 9 volts left. Therefore, there must be 3 volts over here. So, to get our current, V over R equals 3 over 60. Easy. And the other thing about diodes is you can't put them backwards. Tisk, tisk, tisk. So when we're going through here, we imagine our current. It's going along. And it's like, hey, I got to go through all of them. These are all on. I should probably tell you the question. He puts them backwards. Which one of these lights are now on? Hey, but we just did that. And we're like, all of these are on. Now we know this one's going backwards, so no current flows through here. But that means we can't get our current going through this one to here. There's no current going through this entire pathway because it's blocked off. Well, there's no current in here, no current in here. Off, off, off. Okay. Light emitting diodes. Photodiodes. We can use them in 2 ways. That's the interesting thing. I call them solar panel mode and light detector mode because it makes sense. Photovoltaic mode confuses me. Photoconductive mode confuses me a bit. But here, solar panel mode means it's the battery. It's the battery. And this is the output of the battery. So we call it neutral bias because there's no current flow from somewhere else. This is making the current flow. It acts as a battery, and we just use the graph to figure out how much voltage, how much current there is. So example questions like, what is the maximum voltage of this photodiode in photovoltaic mode? And you're like, it is this number. That's the maximum voltage we can get. What's the maximum current? It is this number. That's the maximum current we can get. What's the maximum power? It is around here. And we get the best voltage times current, usually around that point. And those are most of the questions. They could probably ask resistance as well, or how much load is resistance, and then you just go voltage divided by current, and different things like that. Okay? That's pretty simple. I can't find a question to show you, but it's not too bad if you just look at that. You can look at past papers and the physics. Some of the physics books are pretty useful. So the photodiode in photoconductive mode is when we want to use it as a light detector. So here we put it in backwards. And the reason we put it in backwards is now it acts as a current gatekeeper. If you shoot light onto here, it's only going to let a few bits of current go through. Not much. Okay? And it only goes in, it goes through backwards actually. It's pretty cool. And most of the time it just blocks, like we said in the LED. Usually you can't send current the other way. But here it's special because you shine light in and only a few bits of current go through. How much goes through, you ask? It's according to this graph. This is the current. You have this much going through, like 1 milliamp or 2 milliamps, and it depends on what kind of light you shine on here. Another advantage is it's fast. I won't go into the reasons, but just know that photodiodes in reverse bias are fast detectors of light. Fast detectors. So I'll give you an example question. Yeah. Shows the current through a photodiode for different values of power in megawatts of the light falling on it. So this is, we have a photodiode, and it's going to look something like this. Here's the circuit. See, there's the light going in. And now we have to figure out how much current is going through. Use the information in figure 6 to determine the voltage across the 2 kilo ohm resistor in figure 4 with the power of the light falling is 10 milliwatts. So first, we just need to convert this to something we can use, because right now it's a photodiode. I don't know anything about photodiodes, but I know 10 milliwatts. 10 milliwatts. I just read it off the graph. That means we have minus 4 milliamps of current. If we have minus 4 milliamps of current going through this, what's the voltage drop? Minus 4 milliamps going through here will tell us that it's minus 4 times 2 gives us minus 4 milliamps. Minus 4 times 10 to the negative 3 times 2 times 10 to the 3, that's 2000, gives us 8 volts. There'll be 8 volt drop across here. Not too bad. And that's photodiodes. So, special resistors. We have temperature-dependent resistors, and that's usually high temp, low risk, and low temperatures give you high resistance. And high light, light-dependent resistors, which usually give you high light and low resistance, low light and high resistance. It's good for modulators. Just know that. I'll explain to you briefly, but basically you can use either light-dependent resistors or photodiodes to receive information from modulators, and modulators probably scare the heck out of you, but I'll talk about that in a second. Basically, just treat them as normal resistors and you use the graph. I will find an example. Here. This is resistance against temperature, so we know it's a thermistor, a temperature-dependent resistor. They call them thermistors. What is the resistance of the thermistor when the temperature is 20 degrees? Let's go along. 20 degrees, resistance is 15,000 ohms. Using the thermistor, the 6-volt battery, and one resistance from the listed resistor, draw a circuit that produces a voltage greater than blah 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 blah. Okay, so using all this, we just take the fact that at 20 degrees, our thermistor's resistance is 15,000. So our thermistor, our confusing symbol that looks like that, is now just a resistor, which we know is 15,000 ohms at 20 degrees. And when it gets hotter than 20 degrees, the resistance goes down. Okay, so when greater than 20 degrees, resistance goes down. And now it's just a regular resistor, and we can just put it in 15,000 ohms, and then we just connect it, and we draw the circuit. I'm not going to fully do the question, but that's how you can use it. You can look in thermistors later to see the full answer. Easy. Easy peasy. Amplification, it's not hard. Only 4 things to know. Gain is the gradient. So you take the gradient and that gives you the gain, which is V out on V in. Pretty handy. 1. 2. Inversion means there's a negative gradient. It means anything coming up will become down, anything going down will become up. So it looks like that. Operating point is the midpoint of the linear region. The linear region is very important. That's where we get the gradient from. And clipping is if you go beyond that. If you go beyond that, the amplifier won't work properly. So I need to give you a quick example. Here. So this is our voltage amplifier. I can already tell you the gain equals V out on V in equals 4 volts on, so I'm going to take this point. So this height is 4 volts, this distance is 10 millivolts, 4 volts on 10 millivolts equals 4,000 volts on 10 millivolts equals 400 gain. So I know the gain is 400. What else do we need? Inversion is not inverted because it's a positive gradient. Operating point would be here, and clipping will happen if we go beyond 10 millivolts on our input, which we don't. So there no clipping will occur. The axis, draw the graph of the output voltage against time. Include a scale on the voltage axis. Okay. So the graph will look exactly the same because we're not inverting it. Also, no clipping is happening. So it's going to look like this. Now, what is the maximum height of this? We put in 5 millivolts. That's going to give us a maximum of 2 volts out. So let's call it 1 volt, let's call it 2 volts. So I know it's going to look the same. It's going to go up to 2 volts. And there's no clipping occurring. So I can just draw that. Now let's pretend for a second this is not 5 but this is 15. Now, if we put 15 in here, it's going to be clipped. So it's probably only go. So we have to draw it. We know it's going to be clipped. Where does it start getting clipped? When we get 10. So we should put in a line here saying this is 10 millivolts. 10 millivolts. This is about where it's 10 millivolts. So that's where it's going to get clipped. So now it's going to look the same. It's going to look the same as this because it's going to get clipped here at 10 millivolts. So if we input 15, going to clip clipped. I'll show you what it looks like. It's a new graph. Let's pretend this is now 10 millivolts. Minus 10 millivolts. It's going to get clipped here. It's going to look the same. So it's going to go here. It gets clipped. Comes back down. Back down. Gets clipped. Goes back up. Gets clipped. Goes back down. Gets clipped. Goes over here. And that's how you do gain and clipping. Amplifiers. Easy. Now, modulation confused me for a little while too, but it's not too difficult if you understand what they're really trying to say. Essentially, modulation is encryption. Okay? I have my message. This is my message. And I set it into my microphone. And now I have a source. They can call it the radio frequency source, they can call it anything, but it's like a code. It's a way of converting my message into some kind of secret message that no one can read. The carrier wave is a secret coded message. So this is my message. This is the code. Okay? And when we combine them, we get something that looks like this. So it looks just like my message originally. That's what it should look like. Yeah? You can see that there? But no one can read it, because now it's all messed up with this code. And then when it gets to the end, it gets decoded, and we get my original message. So I'm going to find an example of this question. So this is pretty much exactly the question. Large constant value, so we're going to convert it to our RF source. Here's the modulator. It goes across and comes back and comes out the speakers. Shows A, B, C, P, Q, R, S. What's going to happen? At A, this is our message. Messages look like this. At Q, that's our source. That's our code. Well, it's a code. So it looks kind of like that. It's kind of weird. No one can understand it. And now we combine them together to get our coded message at R, C. And then we uncombine them to get our message out, and it's our original message. We can use this with light. We can do this with sound. With light, the only thing is, usually we can have positive and negative. This is our message. This is our input signal. But light, you can't get negative light. So what they do is they just move it up. So this would be our carrier wave. So here's an example. So I'll quickly tell you the situation. Where's the sliding circuit? LED circuit. Okay, so this is the variable resistor. Move this back and forth. It changes how much light is coming out. This is our initial message. Yeah, that's the resistance. Then it says, and I draw the variation in the brightness of the LED with time. So, if we have more resistance, there'll be more voltage absorbed here, there'll be less voltage here. That means if there's less voltage, there's less light. Or less current. The message should go the other way. I don't know exactly how it's going to look, but I do know it's going to be something like that. And because of that, here is our message. Here we convert it to a carrier wave, which is light. And then the receiver circuit decodes our message. Decodes it. So this is our message. Here is our carrier wave. And then something's going to decode it. And that's cool. It's pretty cool. Okay. So I think that's pretty much all of electronics. Hope you enjoyed it, and good luck for your exams. Don't stress too much. See ya. So I'm back. A few things I need to clear up because I made some mistakes. First of all, actually only a few small ones here. Modulation. This is the carrier wave. This is not the carrier wave which I said before. That's not the carrier wave. This is the carrier wave, and it is the code. And this is the coded message, and we call it the modulated wave. That makes sense because it's the message that's actually been modulated. Carrier, the code is the source. Modulated wave is the one including the message because it's been modulated now. It's been encrypted. Okay. A few other tiny things. This here, which I said before, it's not 10 millivolts if we made that situation up. If it's not 10, that's the input. The output would be 4 volts. That would be 4 volts. And that would be minus 4 volts. And on our diagram over here, last thing it says, the LED stays on. I didn't read that the first time because I've just been skimming everything. And because the LED stays on, that means we don't get a light value of 0. So it should be slightly above 0. Or it could be, it doesn't really matter how far above 0. But as long as it's above 0. You have to read, guys. Read. Don't be like me. Bad. Okay, now relax. Now go take and just do whatever you want. I'll catch you guys later.